Welcome back. I hope everybody's refreshed now. We get another very cool input from Felix Berkenkamp. He did his PhD at the ETH Zurich under Andreas Krause and who was with
Angela Schölling.
Angela Schölling, yeah. And I learned to know his name when I was using years ago the library SafeOpt. And then I read the first time about him, and so I was excited about this work, and I'm really excited that you're here now and give a presentation, and I hand you over the stage, please.
Thank you. So when I first accepted to give a talk here, I asked a bit, what's the audience? And I was told, well, clearly we have experts in reinforcement learning. They really understand these methods. We also have people who have no clue about reinforcement learning. They just want to learn about it. And we have practitioners who care about how to actually apply these methods. And so if you give a really weird unconstrained input, you get a kind of weird unconstrained output. So this talk is going to be an interesting mix of opinions, best practices, tips, things I've learned when applying reinforcement learning, but then also a bit of methods and understanding a bit what's behind these algorithms, and we'll end up with like one cool trick also that we've used quite a lot at Bosch on how to deal with when your simulation or something you have on your reinforcement learning side doesn't match reality. So working at Bosch, we really care about real world problems. And so this is one instance of a real world problem. So every winter, lots of people from Bosch fly over to close to the Arctic Pole in Sweden. So I was there last year, and they test their cars on snow conditions. Right, so you want to make sure that your car is actually, for example, brake or like your traction control system, that all these control systems in your car actually work when you drive out in the real world. And the only way to test this reliably is if you actually have lots of snow. And so up there, they have like large lakes that freeze over in winter, and they test these cars on these conditions. And this is extremely cool. It's also extremely expensive, as you can imagine. Right? Just maintaining that facility up there and having all these people fly over, have the cars transported all there is extremely expensive. And so one thing that we are interested in is, can we make this more efficient? Can we actually save money using reinforcement learning by automating some of these processes? And as much as I would like to talk about like these actual real-world applications, it's actually somewhat one limiting factor of working in industry is that you often cannot. So I will talk a lot about like different tricks we've learned, but I can't actually in some cases tell you what's the specific application that we've worked it on. Just know that everything I will talk about comes from one of these really cool real-world applications. So if we look at these real-world applications, right, they're all reinforcement learning environments. They're actually like driving cars. You can send them actions like controlling your wheels or your steering wheel or whatever in your car. And you get out some information, right? You've all seen this plot probably a million times. And our goal is always the same. We want to find some parameterized policy that maximizes some notion of reward, some notion of performance. And what's really cool about this framework is that if you look at these real world conditions, I don't actually have to understand them thoroughly, right? Reinforcement learning is the switch from understanding your problem so deeply that you can write down the solution to your problem, your controller. And it's a switch to understanding, like only specifying what it should look like. So you specify what is a desired solution, and you let kind of the algorithm do the hard thinking and figuring out how do I actually get to this, right? What is the optimal policy? So conceptually, this is a really, really nice framework that it actually, for me, makes things simpler, right? I don't have to think about the limitations of whatever, like linear models or so, or I don't have to think about, do I understand this system? Can I model it somehow, this interaction, such that I can solve it? But in principle, it's a framework that lets me think about solutions. This is super powerful. Now, the problem is, as a community, we spend quite a bit of time not looking necessarily at the real problem, but we're looking at like very simple Mojoko simulations. And if you actually go to these real world systems, you realize that a lot of the assumptions that we bake into our algorithms, a lot of the benchmarks that we profile on and really tweak for performance, they don't necessarily match this, these kind of simulations. And so one thing that's maybe the most obvious is that a lot of reinforcement learning actually works with exactly this graph here where you have state information. And in the real world, the first thing that you notice is this is never the case. So you're always acting in partially observable environments. You always have an internal state in the environment, but you don't know it fully. There's always something that you do not know and that you need to figure out. Okay, so this means that already, like, we need to change our policy going from just states, and we have to switch to just working on observations. And we'll see a little bit about the consequences of this later. But let's say now we have these algorithms, right? Like, it's not like the community hasn't worked with partially observable environments. I would say like 80–90% or so of the literature is in MDPs, so fully observed environments. But you can use the remaining 10–20%, right, and work on these partially observable environments. So what now about my real car, right? Can I just do this? Can I just take my reinforcement learning algorithm now and finally get to work on my real system? And the answer is, as we've already heard in the previous talk, this can actually be a bad idea for a bunch of reasons. Right? So one is data efficiency. I mean, we've seen previously that it's possible to learn relatively quickly. But there are some constraints there, right? You get data constantly, you can change your policy constantly. We'll see later that's not something you can often do in real world systems. Random actuation, we already talked about it. Apparently there's a great solution coming for this, but random actuation on real world systems is a really, really bad idea. Like, you break your robots, they're all low pass filters, so you actually don't see the effect of your noise, so you have to actually pump in even more noise. It's just really not great for the system. And if we go to somebody who has like some real car and we say, well, can we just apply high frequency noise to your control inputs? They're just like, no, we build safety guards around this so that you cannot. So actually for our systems at Bosch, often if you actually put in like a high frequency reference signal, there's some logic in between that will just cancel this out and completely ignore it. You will never see the effect on the real system. The third thing is, and this is actually really important, reinforcement learning optimizes for the system at hand. Like, normally, if you think about computer science, it's all about generalization. You have a train set and a test set, or like a validation set. And like, what you never kind of try to optimize on the same thing, right? Like, you never train on your validation or test set, but you use those for evaluation. We don't have this in reinforcement learning. In reinforcement learning, we only optimize for the system at hand. And that also means we don't have any guaranteed robustness settings. So what does this mean for a car? Let's say I'm optimizing something like some safety critical system, let's say like a braking system. What tells me now if I learn a controller there, what tells me that if I optimize this now and it brakes really nicely, nothing tells me that if I now go to different conditions that it will still work there. So just optimizing for some nominal condition on the real world, it's not really enough. And the last thing is that actually these systems are kind of safety critical. So at least you want to make sure that during and after like learning, things remain safe, like you validate some constraints. So what do people do, right? It's not like reinforcement learning has not been applied. And so one thing that most people do is they sidestep these problems altogether by building some simulation, some approximation. Right? And then in this simulated setting, you can now do whatever you want, right? Like, we have really, really good algorithms and really, really good implementations that, given a simulator, you can really learn efficiently. And one thing that's really cool in simulation is you actually have complete control over your environment. And this is like what people then do in practice is they will actually change the conditions of their environment and make the policy adapt to them. And this is one thing that's often missed. If you do this, this is kind of then called meta reinforcement learning. The only idea of meta reinforcement learning is that you change the physics of your simulator in a sense, you change your task, and then you still train a policy. But if you really want to do this, you now are definitely acting in a partially observable environment because you don't know the task that you're operating in. And that means you need to have a policy that infers this task from data. So you need to have some recurrent policy that acts on past observations to figure out what exactly is happening. Okay, and this is essentially the state of the art, I would say, if you really want to transfer like from like solve some task on some real system, is ideally have some simulator that's pretty decent, maybe work to improve that simulator, randomize over the physics so that you're robust to different situations and maybe account a bit for the inevitable error in your simulation, and learn your policy there, and a policy that can adapt. A policy that works on past observations to figure out what to do in the current world. Now, the one downside of this is that the way back from simulation to the real system is kind of luck-based, right? Like if your simulation is great, it might transfer. If your simulation is poor, you might still get lucky. But in general, like we know from even linear control theory, that an optimal controller for one system, even under very, very small changes to your system, could become completely unstable, not work, have low performance. So there are no guarantees in a sense. And this is kind of annoying, but it's also kind of motivating, right? So it means that right now, it's a bad idea to plug in reinforcement learning into real systems, but there are actually paths that we can work on. So for example, to look at data efficiency and like this random actuation, we could think about how do we design better exploration schemes? Do we have better algorithms? Maybe we can do something like model-based reinforcement learning where you don't have this. And for the second part, it's all about safety, exploration, and meta reinforcement learning, and thinking about kind of how to actually, let's for example, if you have a simulator and you can actually learn a robust policy there, how do you can actually transfer this kind of robustness property from an imperfect simulator to a real world system. And I'm not going to claim that I have all the answers here, but what we're going to talk about today is mostly this first part. So kind of how to actually apply reinforcement learning and how can we deal with, for example, sim theory gaps and errors. And now comes the first intermezzo, if you want. So it's now going to be looking a bit at if we actually apply our algorithms to these real world problems, what matters? Like what algorithms do we have? What flavors do we have? And like weird things that you might encounter or common issues. Okay, and for this we actually need to understand a bit the methods. Right, like reinforcement learning, I think is really important, is not a black box that you can just apply. I wish it was, right? I think we should get there eventually, but right now it's not at the space where somebody just gives you an RL algorithm and you give it its problem and it will magically work 100% of the time. Right? Like there are methods like this out there, convex optimization, like that's well understood, but reinforcement learning is not there yet. And this means that we need to understand actually the methods and their shortcoming in order to apply them. And so for those that have never seen reinforcement learning, let's, like in one slide, very briefly, what do RL algorithms do? So let's say we have this kind of toy system, just a single state, and we're actuating the system over time, and we can generate data. So here you kind of see one trajectory that we might generate with such a system. And we can do this a bunch of times. So for example, we can have a stochastic policy or so, and then we can generate different trajectories. And now what the reinforcement learning algorithms do is they look at each state, right? So a state being just one horizontal line on this plot here. And for each of those states now, we've tried a bunch of different actions. Right? These blue dots here represent different actions that had different effects given the same state that we've encountered in this example. And our reinforcement learning algorithms have the task of figuring out which of these actions, these different actions that I've tried in the state, which one was actually better than the others. So they look at all these actions, they plot them essentially on a different plot. So here you have actions on the horizontal, and then forget the vertical for a second. And we have a distribution over actions, which is this Gaussian distribution, which led to the different actions that we applied in these blue dots. In particular, these blue dots are just samples from this distribution. Right? We had a policy where at each state we tried different actions, and these are just samples from this distribution. And so far, all we've done is we've taken the data that we've had and we've plotted it in a different way. And the RL part, the reinforcement learning part, is essentially only happening now, and it's a very simple step. You look for each of these actions, how good were they? So it's called policy evaluation. And in this particular class of methods where you're on policy, so you've generated your data with the same policy that, with a fixed policy, this is super easy, right? You can actually just look at empirically what happened after I applied this action, and you can sum up all the returns. It tells you how good a particular action is. This gives you a ranking here, right? Like each arrow telling you kind of after this, how good was my action, right? Like how much reward did I accumulate? And like I said, value here just being the empirical return, like looking at the data, how much reward did I get? And then reinforcement learning does nothing other, like all of reinforcement learning on policy methods do nothing else than now trying to fit a new policy distribution, a new distribution over actions that is more likely to yield actions that had higher return. This is all there is to reinforcement learning and on policy methods. There are different tricks and pieces and different algorithms. Specifically, we really like to give new names to algorithms, but this is like the core idea behind everything. Okay, and this is why on policy algorithms are like so easy, is that computing these values is extremely straightforward. And you can go along one step further, right? Like right now we had a policy and we sort of collected data with it, but these on policy algorithms, you always throw away all your data. And so what people like to do is, well, they like to be more data efficient. So they now collect data, like all your past data, and you suddenly try to learn with this. So you've kind of changed your reinforcement learning problem. You no longer have a policy that's directly acting with it, but now somebody is giving you some amount of past data, and you're using this in order to optimize your policy. And the key challenge now is that previously estimating the values was really straightforward. This becomes more challenging. And in particular, one thing that becomes really challenging is if you have partial observability. So what we have here is a sequence of data from the real environment. So we have a sequence of observations and actions. And you want to find a policy that acts on this in order to identify what's actually the true state of my environment. Right? So we might actually just look at one particular state action pair, kind of throw away what comes afterwards. And we want to ask kind of what should I have done instead of action 3? Right? Reinforcement learning in principle is a complete planning problem where you have to optimize all the actions. And the clue is that we're condensing this into a problem where for each state, we ask what should the different actions be. And in particular, like at the core of these reinforcement learning algorithms, like if it's a deterministic algorithm, at least in this particular case, internally you solve this kind of optimization problem where you have some function Q that gives you this measure of how good things are. So a value function, for example, and you're trying to find the action that maximizes this. And now the problem you have is that this depends actually on the state, and you do not know the state. And that's the key difference between a partially observable environment and one where you can observe everything. There's a very simple solution to this. In particular, what people do is they learn some kind of inference network. And so you give them all the past data. You have some LSTM or some recurrent network that has an internal state. And you use that to figure out the current state and act based on this. And this is super exciting because it's actually a very simple method to take your partially observable problem. But once you have some LSTM or so that figures out the current state of the environment, you can apply your standard reinforcement learning algorithms again. So kind of lucky here, right? Like we can apply all the algorithms that we developed for MDPs, for fully observed environments. And the only change we need to do is figuring out, like having some network that runs over the past data so far and figure out the current state, and then we're back in the normal operating scenario. And you can train this end to end, and it actually works really well. There's just one gotcha that actually a lot of people get wrong, and that is, so in an MDP, so in a fully observed environment, right, we have these critics or these policies that act based on the state. And a lot of implementations that you see out there, what they do is for POMDPs, they do this. So they say, well, perfect, all I need is the past sequence of observations, and I can now solve my algorithm. And this will not work, right? So this is actually not enough to solve your reinforcement learning problem. Because if you look at this, my current state here depends actually on the past sequence of observations and actions. Right? Like if I give you a sequence of observations and actions, that's maybe enough to figure out the current state, but just the observations in general are not. And so what you actually need to do is you have both your policy and your critic in partially observable environments need to depend not only on your past observations, but they also need to depend on your past actions. And this is like really like a lot of practical implementations that you see online, they actually get this wrong. And maybe for like the more reinforcement learning interested people, this is also true on policy, by the way. Because on policy, if you don't give the past actions, the best your algorithm can do is figure out the distribution over past actions, but it can't know the exact actions that were applied, which are needed to figure out the state. And so if you're applying reinforcement learning in the real world, it's bound to be a partially observable problem. Please make sure that past actions actually feature in your policy and in your critic, because without this, chances are you're going to lose a lot of performance. It's really, it's like day and night. If you don't add past actions into your policy and critics, you really struggle to learn in partially observable environments. All right. So the last thing now, we've done off policy, right? We've now figured out how to learn in POMDPs. The last thing you might want to do is you might want to do model-based reinforcement learning. That means kind of before we just had data and policy optimization, and now what we're adding a step in between where we're doing model learning. And this gives us the ability to generate new off-policy data. All right, like I've learned a model that, given a state or an action, allows me actually to answer this counterfactual question of what would have happened if I applied this different action. And this is really powerful in principle, right? Because it allows me to generate lots of new data cheaply as a proxy for the real environment. It's like a simulator that you learn online. And so I just want to give a little bit of perspective on how I see these three classes of algorithms that we've seen so far. Right? So we've seen on-policy algorithms, and they're extremely reliable. Right? Like if you give me an environment and a reward function, chances are you can just apply, take stable baselines, apply PPO. This will probably work really, really well. But they're also really easy actually to use with recurrent policies. Like on policy not only means that your actions are on policy, but also the state of your recurrent network is also on policy. That makes it really easy actually to implement these algorithms, and very also cheap in a sense. The only downside is they're extremely data inefficient. You don't actually want to use this ever on a real system, but if you can, you definitely should. Right? If you have a fast simulator and that's all you care about, stop here, right? Don't go any further. And so then there's the next class of problems, and that's like off-policy algorithms. Think like SAC, TD3, QDrop, or whatever we heard just now. Lots of new names for like very similar algorithms with like little tweaks. But a general class of off-policy algorithms. And here we've already gone like one step from being on policy, where things were really straightforward. Like value estimation is just as easy as summing up returns. That gives you an unbiased estimate. Now we go off policy and we've introduced a new problem in our reinforcement learning pipeline. Namely, suddenly we have a critic that we need to learn. Right? Like we have like given data, we need to figure out how good are different actions. And we have good algorithms for this, but we've added something new in, we've made the problem more challenging, so you can't expect everything to only get better. So these algorithms are more data efficient, but suddenly like the quality of this critic really matters. Right? If you learn a good critic, it's as easy as on-policy reinforcement learning, but learning the critic becomes the new main challenge. And that means you've kind of made your problem more challenging, you've added something on top, a new degree of freedom if you want, and that also means that your algorithm is going to be more complex, and there's a higher chance that it might fail, just because there's one more degree of freedom in there. So if you can avoid it, don't, but if you need data efficiency, well, then you have to deal with this. And so one thing is, on policy, it's very easy to learn recurrent policies. As I said, the state of your recurrent network is also on policy. Here you actually now need to spend quite a bit of more compute, because you need to actually roll in your critic. You start from a random state, essentially, for your policy, and then you figure out over time kind of what's actually the state of the environment. So it's a bit more challenging to implement, a bit more computationally heavy too. And then the last one is model-based, and essentially the only thing we've done is we've taken the way that most people implement model-based algorithms these days is you learn a model, and then in principle, right, it would be really nice if we could just use our really data inefficient algorithms and apply them to the model. The problem is our models are actually not good enough to just apply on-policy algorithms. Like this would be really great, right? I learn a model, I do a full rollout, and I can now use my really reliable on-policy method. But the problem is our models are biased. They have errors, and we know they're an approximation of the real world. So what people do is they only do relatively short rollouts because model errors accumulate over time. And that unfortunately means that you're kind of bound to using off-policy methods. And that essentially means you've added one more problem now to your entire pipeline, right? Which means that not only do you have to learn a critic, but you also have a model and you know this is wrong. So if you added one more degree of freedom, which is making the problem more challenging overall. And then so one thing that's really nice about these model-based algorithms is that you can encode prior knowledge. And this is in principle super powerful. But just from like my experience, you have to be extremely careful here. It's very easy to encode too much prior knowledge that's not actually there. So you're kind of removing the degree of freedom to model the complexity of the real world. And it also, these hybrid models can actually be more difficult to learn than just a simple neural network. So you need to be really careful when dealing with these methods. So as a general guideline, like we've heard this in the previous talk, start simple, that also applies to algorithms. If your method, or your problem at hand allows it, start to the left of this plot, right? The simplest, most reliable methods, and only go to the right-hand side if you really need it, right? Only go off policy if you actually don't have a fast simulator. Only go model-based if you're really need it. At least kind of empirically. Oh yeah, and so one thing, so when you do model-based RL, and we do that actually quite a bit at Bosch because we really actually need the data efficiency. Usually the most difficult part that you should spend time modeling is your actuators, because all of these methods, these algorithms, they act on actions. And if you're kind of the actuation pipeline, the one that maps your action to what actually happens in the system, if that is wrong, so will be your reinforcement learning algorithm. All right. Now, one thing that's, so I'm getting to the end of the kind of random section of like random ideas and things about the methods. One thing that also in real world is very different from like typical machine learning research that we find is that we don't actually have a gym environment interface, right? Every talk starts with just give me a gym environment and I can optimize it. And we can never actually do this. I have yet to find a problem at Bosch where this is actually viable. What we have instead are controllers that run on microcontrollers. No way to get the data really out. I mean, you could spend the time to do that, but nobody will actually take that money just so that you can get your data back in real time. And so what you actually have in practice is usually a separated data collection pipeline, where kind of your algorithm gives you a policy or policy parameters or some compiled policy, anything that kind of goes into a compiled C binary on the real system. Then you run that system in the real world for a fixed amount of time. You collect data with that policy. So actually collecting data on policy in this particular case. And then you get the data back at some point, and then you get to do reinforcement learning. And suddenly you're in a kind of offline reinforcement learning setting, in a sense, where you are just given the data that you have, and you're trying to find the best policy that you can possibly find. And this seems conceptually quite similar to standard methods, but if you actually look at SAC, this really works best if you can change the action at every time step, right? Where you can kind of continuously change your actions and continuously gather feedback. Most implementations work by optimizing for a bit, finding a new policy and changing the action and plugging that again into the system. So kind of policy optimization and actuations interleaved. And if you actually go away from this, you have a bunch of new problems. So one is like these methods become actually a bit less data efficient. The second is we're actually in an offline reinforcement learning problem. And there are offline reinforcement learning methods, but I've yet to find one that I enjoyed using in practice. And there's one thing though that's special about the setting that actually makes this really easy compared to the standard offline reinforcement learning setting. So standard offline reinforcement learning setting, people assume you're just given data and you try to find the best policy. Here we actually have a bit more information because we know that we've actually collected data of policy. We actually have the last data generating policy available. And so a very simple trick that helps in these kind of settings is to actually add a trust region. Take your SAC algorithms or whatever kind of off-policy algorithm you want, and actually add a trust region to say, I want to stay close to the last policy. It's very special to this setup. You can't do this in general offline reinforcement learning, but in this particular setup, we actually can, and it does help to make things more robust. Because now I can train for as many gradient steps as I want on the given data, but by actually having a trust region, I don't have to worry so much about like running far away from the data, which normal SAC would actually do. Right? There's no trust region there. All right. Oh, I wasn't at the end of my general section. There's one more reward. Luckily, we talked about this already. So one more thing that's different in real environments compared to, like, let's say Mojoko, is that normally in reinforcement learning academia, we assume that we're given the environment, right? Like somebody gives you a often simple system, like an environment and a reward function. And typically that reward function was already designed for the problem to be really easy. All of the GYM Mojoko environments were designed to work well with on-policy RL methods. That's where they originated. And that's why you don't need any principled exploration, just a bit of noise is enough. Essentially you need to estimate a gradient and you can do gradient ascent. Like Mojoko is even fully differentiable. You could get that gradient analytically if you wanted to. And one thing that's really important is you can actually, even on very simple environments, you can make algorithms fail catastrophically if you don't define your reward properly. So for example, here's a soft actor critic running on a card-pull swing-up task. It's a sparse reward, right? So I only reward it once it reaches the top, no problem, right? I've omitted the scale at the bottom, doesn't really matter. But SAC just really reliably will solve this even with a sparse reward. But it's very easy to break this, right? If you take now your reward and you add a cost on actions, which normal Mojoko environments don't have, suddenly these algorithms will fail catastrophically. And the reason for this is that they don't do exploration, in a sense. They just try randomly. And then we've seen before, they look at their actions, look at their value functions, and say which one had the highest return. And now actuation cost counteracts the typical exploration, which is entropy based, right? It's like try out a lot of different actions, but my reward is telling me, yeah, no, don't, right? Like you actually don't want to try like really large actions. I have a penalty on actions. And in the sparse reward setting now, initially I only see kind of data that never reaches the top. And my actuation cost is telling me, don't actuate the system, this is expensive. And so these algorithms, they increase in reward only until they figure out not to do anything with the system and they never swing up the pendulum. So you actually need to understand your problems and you need to be careful about specifying the reward. And especially if you have sparse rewards, be really, really careful about action costs. And so here's kind of just in practice, how would you kind of approach this? So we have a partially observable environment. And this is kind of a thing on its own, right? Like we already given the system. And actually for us, the reward function is usually a tuning factor. And in general, right, the reward function could depend on the state of the internal environment. And then the environment gives you out the reward. And I've yet to find a real world problem where this is actually necessary, right? For us, at least always, the reward actually only depends on the observations. Right? It doesn't actually depend on the internal state, because if I knew something about this internal state, I would usually give it as an observation to the policy because it would help. So for us, actually, the reward function is something that only acts on observations and actions, and it's a tuning factor, and it can potentially now vary over time, right? I've mentioned this setting where we have data collection and then we optimize. Well, during this phase, we can actually change the reward function. And actually, this is not what I wanted to start with, but okay. So you can, so if you pick a reward function now, we already heard this. Definitely, like start with a dense reward, something that tells you something about the quality of observations at every time step, ideally. And bounded rewards, really important. You can't normalize unless they're bounded. I think like a lot of people coming from control would start with, let me specify a quadratic or so. This works really poorly because it's not bounded. Like we already heard the solution, just take an exponential function or something like this. but make sure your rewards are bounded. Then, like I said, so take observation-dependent rewards and start with something that doesn't have action costs, because if you're not careful, these action costs can really hurt the entropy-based exploration of these methods that lie underneath. And then you can change the reward function over time, right? You don't actually need to learn from scratch every single time. And what's really cool about if your reward function only depends on observations is that you can go back and relabel the data, right? I've collected past data with rewards. I changed my reward function. I can relabel now what the rewards were. And we do this a lot. It's really, really useful to be able to go back, have past data, and don't have a reward that has some internal notion of state or came from the system, but just have it as something that actually depends on the observations. It's really nice to be able to use past data and just relabel it, and then use that to warm start your kind of next learning iteration. We already heard this, like be really careful about termination signals and the rewards that you give at these termination conditions. Like so for the first 5 years in reinforcement learning, just by the design of the most popular library, GYM, actually most people didn't achieve peak performance on their environments just because they confused termination and truncation. Don't have to talk about this because we already heard about this previously. But like another component to it is that the rewards that you give when your environment terminates, you have to be very careful. It's very easy to encode unexpected behavior there. And what do I mean by this? So let's say my goal is to go to this wall, and I give myself a reward for, not falling over. Great, I'm a humanoid, right? Problem solved, locomotion. And then there's also a reward for reaching the goal. And now if the reward for reaching the goal, where my task terminates, is too small, the optimal solution for going there is, you go there and then, well, no, right, you go back. Like the reward for staying actually alive and not falling over is higher than this one-time reward of actually reaching the terminal state. So you need to be really careful when encoding the reward for termination because it's fundamentally somehow different. So in general, if you want termination, you should make sure that your reward at your final state, like where you terminate, should be higher than the maximum return you can achieve. So if I get reward for not falling over, then the reward for reaching the goal should be higher than the cumulative reward I could gain by not falling over. And if you don't want termination, well, then it's the other way around, right? Like you should make sure that the reward there is actually smaller than what you could achieve by just normally interacting with the system. And then finally, if you really struggle with this termination, there's a class of methods called constrained reinforcement learning that's not trying to encode so much in the reward, but tries to deal with this as a separate constraint. And if you're really struggling with this trade-off between rewards and your constraints that you're encoding in the termination, you might actually want to look at this class of methods that can actually be easier to work with than really twiddling with these termination criteria. All right, so I will not keep you too long. I know there's lunch coming. So now I would talk about, just for 10 minutes or so, talk about one trick that we generally use, that we found to be really useful in practice, that I think also might actually be useful for some problems. But before that, maybe some questions about the general kind of, wild drive through methods and random thoughts about reinforcement learning. Any questions so far? Yes.
Sometimes in the real task, the reward is a real measurement signal which contains the latent variable. So is it okay to include the reward also in observation?
So, okay. So this is if you follow what I just said and your reward depends on observations, this is a non-issue because there's no extra information gained. I think what you're referring to is, especially if we train in partially observable environments, some papers advocate performance gets better when we train on rewards. And the reason for that is exactly this. So for example, POMDP, the favorite benchmark problem is remove the velocity. Right? That's just one part of your information that you're omitting. And now quite often for locomotion tasks, your reward is the velocity. And unsurprisingly, if you now put the reward back into your observations, you're no longer in a POMDP. Yay! It's really easy suddenly. So I think Academically, yes, use everything there is. In practice, like I said, for me, reward functions only depend on observations, and then that question is irrelevant because the observations already contain all the information to specify the reward. Yes.
So I'm one of the non-RL people, so a basic question. So when you're talking about the off-policy learning, if you have a case when your reward depends on multiple steps, multiple actions. So I get some pair that's like, oh, I'm in some state and I take some action, but now in order to get my reward, I have to take multiple actions. But now this is a computationally intractable. Like I'm never going to have enough data so that like all of those points will actually be in my data set. How do you use this?
Right. So, I mean, your policy can depend on observations. In principle, it can also have an internal state, right? You could accumulate past observations and whatever. If you want to, for example, penalize changing from one observation to the other, you could just store the old observation. But suddenly your reward suddenly, even if your problem was an MDP, by doing this, you're turning it into a COMDP, right? Because like it depends on the history of things. So in principle, yes, your reward can have an internal state, but then you need to make sure that your policy is recurrent to deal with that, and your critic is true.
Basically, you just learn, even if like the thing you care about is your final reward, you learn some heuristic. It's like for each action, you get some.
So, exactly. So you, I mean, it depends really on the concrete problem, right? In the most general case, you could just have your reward function accumulate all the observations and output one final return. Suddenly a sparse reward, much more difficult. Quite often you can find a proxy that's kind of
yeah, like I take a case where I'm trying to walk from here to the end of the room. So I have but I'm taking many steps to get there. So I have some data set of all these individual points. So then I take some step, but it's not the step that's actually in my data set. How do I know what the reward is?
Sorry, just to make sure I follow this. So
like I have a bunch of examples. Okay, I took a step. Like I ran this simulation a bunch of times. I took a step, and I know what my reward was for that case. But now I'm going off policy, and I take a step to get to some new state that I haven't been in before.
Yes.
How do I know what the reward is for that? Makes sense.
But in a sense, right, you're defining the reward function yourself, right? It depends on observations and actions. And this particular case, if you're using model 3, then you can only kind of you're in an observation and you take an action and you kind of don't know the next observation.
Right.
But when you train your critic, you actually don't do this, right? You actually, you do actually know your next observation because you have actually given data. And there's actually not so much. But maybe we should talk about this offline. I think that's...
Okay, yeah.
Any more questions? Yes?
Yeah, maybe I have a question about the offline learning when you constrain the policy. What kind of algorithm do you use there? Is there a common framework? I just know MPO, for example.
Yes, so there's so there are a bunch of methods. I mean, there are a bunch of reinforcement learning that already implements trust regions, right? So PPO does this by clipping. That's one class of methods to implement trust regions. MPO does this a bit more explicitly, right? They explicitly constrain the average KL, and then you have a corresponding dual problem. And then there was actually a paper between KIT and Bosch, where for Gaussian policies, you can actually reparameterize your policy in such a way that you're guaranteed not to violate the KL. If that's interesting to you, I can point you to that at some point later. But yeah, so I mean, it's the typical class of methods that you have in order to constrain.
But these are all offline, soft policy. PPO not, of course.
I mean, it doesn't really matter because you can select your action, like given an observation, you can select on-policy actions for that time step, right? You're just trying to constrain the KL between a previous policy and the current policy, and you have access to both in the setting, which makes it really easy. You can actually compute the KL in closed form if you have both policies, right? You just evaluate the old policy, new policy to Gaussian's KL. So it's easier than actually most normal settings where you don't know your past policy, which makes it really tricky. Okay, so I would go ahead and start with the Oh, why am I going through this menu? All right, and so one thing I want to look at is this model learning, right? In model-based RL. And the key problem that you always have is that there's a bias. Your model is an approximation of the real world. And this is actually a problem, right? So if you take your data model-free algorithms, it's really great, right? You collect data from the real environment. It contains all the complexities, and it's really you're optimizing for the right thing. And the moment you learn a model with whatever fancy method you have, suddenly the predictions of that model are not going to match what you would see on the real system. And this is inherent, right? Like these model errors actually compound over time. And what people try to do is they try to combine these things a bit, right? So maybe they don't. Well, so that plus will come later. But okay, so your model-based, your model actually creates a trajectory that's not a match for the real system. And this has some implications, because in the end, what we care about is improving the policy. And so here, eta is the return under your policy on the true environment at iteration n, so for your policy n, and then n+1 is the policy that you figure out based on your model, the next policy. And now you can deconstruct this term, and whenever you see something like this, like a greater equal sign, and then like a deconstruction of new terms that suddenly appear, you should be extremely careful, because chances are somebody's trying to make a theoretic argument, and this theoretic argument is going to be completely irrelevant for practical application. Because by bounding these individual terms, maybe you can show that it converges, but it doesn't tell you anything about empirical performance. But I'm going to do it regardless. So you can deconstruct this term, and this is greater or equal than the improvement that you get on your policy. So eta tilde here, that's an estimate of how, under your model, how good your policy is. And then because I've added new terms, I now need to subtract them again. And so I can split this up like this. I can split it in what I call an off-policy model error, which is how good is my predicted return under the model compared to the real return for the new policy, and what I call an on-policy error, which is the same thing for my current policy. So again, you can do theory with this, and it's completely irrelevant, but intuitively, if you look at this, what's interesting is that if you compare experience replay, so taking the real data and the learned dynamics, they actually are good at different things. So experience replay is really bad off policy because there is no off policy, right? It's just data. And if you change your action, the data doesn't change, right? There's no notion of this counterfactual of how would my data change if I changed my actions. I just have the actions that I have so far, and that's all there is. The learned dynamics are designed to answer this counterfactual, right? I can take a state, I plug in a new action, and it will tell me it will tell me what it thinks the next state is. On policy, it's completely different, right? Like on policy, experience replay has no error, right? We saw this in the beginning. That's the reason why PPO is so easy. We actually have the data from there, right? Like we can estimate returns directly by just summing up the rewards that we see. But the learned dynamics, well, they have a bias, right? Like even on policy, they have an error. So they're good at opposite things. And if you've ever seen an academic talk where you see this kind of setup, the natural solution is how can we get the best of both worlds? And typically what people do is they try to combine these in a sense, right? So finally, we need that plus symbol. So they try to take the data and do short rollouts under the model. Right, and the idea is that shorter rollout, less time for errors to accumulate. And I want to share one simple trick that we actually use quite a lot, which does something really weird, but ends up helping in practice. And so for this, let's think about this more abstractly. Let's say there is some true function f of x, right? Like some true underlying functions from which I get to see observations 1. And what I have access to is an approximation of this, right? Like f, that's a tilde, yep. So f tilde, which tries to approximate this function f of x, but it's not great, right? It has some errors. And now what I also have is actually a data point. So for a particular x hat, I've actually observed the corresponding value y hat, so the true function value. And now we're going to do something extremely strange. We're going to define a new function that tries to combine the data and this approximation f tilde, which should be orange, never mind. So essentially, here's the idea. If I take a particular input x, I'm going to say, well, the output is just the data y hat, just the observation, the ground truth. And then I'm just going to do a zero order correction, which is the difference between what my model predicts at this new input x and what it would have predicted at x hat. Okay, and this is now a function of x. I can plot it. And if I plot it, I get something like this. So what do I see here? So the first thing, just by definition of this problem, this is still asymptotically correct in the sense that if f tilde is the same as f of x, then this term here, like this y hat and f tilde of x hat, they will cancel out, and I'm left with the true function. So this is already cool, right? If my model is perfect, then I'm also getting back the perfect result. But it has a second property that's kind of nice, which is locally, it doesn't have an error, right? Like by definition, if I plug in x hat into my function, well, then these two terms cancel out and I get the data back. So it's a reparameterization that does nothing other than taking a data point and correcting your model to locally have no errors. And it seems really simple. It's zero order, right? There's no gradient guarantees, nothing. This is all the guarantees you have. But we found this actually helps a lot, and we use this all over the place. So one example, we have policies, and these policies run on microcontrollers. And on microcontrollers, you have slightly different behavior than if you run on a cluster. Just, you know, it's different math libraries, different implementations of methods. You can't assume that they're one-to-one. This is really annoying for reinforcement learning, right? I get data, which could even be on policy, but it suddenly looks off policy by the time I evaluate it on my real system. And so we use the same trick here. So we take the policy, we've seen real data, and we do the zero order correction, and at least on policy that cancels out the errors, and that really helps with reinforcement learning. So it's a very simple trick that we apply all over the place, like I said, for every time we have data and we have a model and we know it kind of doesn't match, we use this trick. And not that much time, don't want to keep you from your lunch break. So I'm going to keep this relatively short. But another place you can do this is you can apply it specifically to a model of the environment. So this is the same equation as before. Now there's an expectation because it's a stochastic model, it doesn't matter. It's the same idea. You have data, that's the true next state you observed. It's an NDP setting for this example. And then you have a model that predicts, given the actual action and state that you put in, what's the next thing, and you subtract what your model predicted on the data you've seen. And so visually what happens is that here's a starting state that I've seen on the real environment. And I've seen a trajectory where kind of given the first action, I went to this particular state, and given another action, I went to next state. This is my ground truth, the real data, my S hat. Now I have a model, right? And I could ask, actually, given the same state and action, what would you predicted have happened? And you can see it doesn't actually predict the right thing, right? There's an error between what the model predicts and what my real data actually returned. And now what I actually care about usually is like this counterfactual question, right? Like if I changed my action, where would I have ended up? And what this reparameterization does in model space is nothing other than compare these two and apply this offset to your data. And so here, we're not asking the model to predict forward in a sense, but we're asking it to predict changes to the data. It's an easier task for your model to predict changes usually than to directly predict feed forward. And you can do this over multiple steps, right? You can now query each point again and apply this offset, and you can over multiple steps roll out this model. And what's really cool is by this property that locally there are no errors, on policy, we just get back the data. If I plug in exactly the same actions as I saw on the real world, on my first step, I'm not going to have any errors, right? My models cancel out. And also on the second step. So I'm getting actually back the data. It's the same trick, just applied to model space. And so what this allows you to do is to go from these partial rollouts to actually longer term rollouts, just because locally there are no errors. And let me at least show you kind of this one example, toy example. So here's a toy example of a linear system, scalar system. I like those. Start simple. Good message from the previous talk. And I've just taken like two fixed models. So it's a linear system, what I call the true system here, and I've defined a reward function, and I can plot the return depending on a policy parameter, also a scalar, great for plotting. And then I've taken my model, right, the approximation that I've defined, and it's wrong, and it actually returns that the maximum reward I get here at minus 0.05 versus my normal model is at minus 1.0. Okay? And now I can use the same trick. I can define my model as a combination of data collected on policy with these parameters here, and the kind of wrong model in the red color. And what you get is this particular shape. And this is now using the model, using full trajectory rollouts and computing the return. And as promised, right, locally there are no errors. It's the only guarantee we have. But somehow empirically, these models are quite good at predicting changes to data. They're not so good at predicting feed forward. So feed forward, right, like just predicting forward with the model, the maximum return was here. But somehow with this reparameterization, even though we have no guarantees for this, right, there's no theory supporting this at all, just empirically, it seems to happen that also kind of the gradients tend to then point in a better direction. So it's a simple trick with very limited guarantees that we found actually helps quite a lot in practice whenever you have this problem that, like, you have data of your real environment, actions, for example, and you have a model, like your policy or so, and they don't match. It's a simple trick that we found actually to help quite a bit. And okay, so there's theory, right, that this on policy error that I showed before goes to 0. Don't have time for this. Here's like just one last thing I'm going to show you before I will wrap up and let you go to lunch. So here's an example of just running SAC and MBPO on kind of Mojoko tasks. Okay, and so if you tune this correctly, this is just using off-the-shelf implementations. Actually, you will find that kind of MBPO does actually quite nicely, and we do about the same. Right, these are tasks where, like this algorithm, model-based policy optimization, from their paper, right? They made sure their algorithm works there. And then we took different environments. So these are the PyBullet environments, and they're re-implementations of Mojoko, but they also changed a bunch of different things, like different initial state distributions, different rewards. They're not one-to-one. And we find that suddenly MBPO, just by default, does a lot poorer. Right? Like it really drops in performance. While this just a simple reparameterization of the model actually is a lot more robust to these changes. And so this actually we find really cool. It's like a little bit you add on top, and it makes your model-based algorithms more robust, at least in kind of our experience. And there's a cool toy example where I could show you why this happens, but we all want to go to lunch. Talk to me like offline if you want to hear about this. So I'm going to skip that and just wrap up. So I think one of the key questions really in reinforcement learning is how to bring it to real systems, and like really under constraints that are actually happening in the real world. And like we have to deal with partial observability. It is actually a key issue, and you have to be really careful there. We saw like include past actions actually in your model there. And how to deal with data efficiency and robustness, I think, are questions that are not fully answered yet, but we have good enough methods that with a bit of understanding and working with them, you can actually make them work in practice. So it's a really exciting time where, on the one hand, I think there's more to be done in reinforcement learning methods to really make them like robust and reliable and really create this kind of out-of-the-box experience. But the methods are also good enough that if you understand them, you can already apply them, which is why you guys are all here in any case. You need to be really careful when choosing your algorithms and rewards. Like I said, start simple, right? Start with methods that are maybe data efficient, but work really reliably, and only add complexity if you actually need it. more or less the same message from the previous talk, right? Start simple. And also with reward functions, you can really, like by introducing action costs, you can suddenly make your algorithm behave in weird ways, in unexpected ways. By specifying the wrong rewards, termination conditions, you can do the same thing. And then we saw like that model-based methods might actually be cool, right? Like allow you to answer these counterfactual questions, might be more data efficient, and they actually are. We use them actually. But the sim to real gap is actually an annoying issue. And so one solution that we saw, this was this last trick, is to ask your model not to predict forward over time for a long time, but answer the simpler question of given data and now a new action, how would my model predict changes to this? And even zeroth order, that seems to help a lot. And like I said, it's a trick that we actually use quite a lot. For example, when our policies from the microcontroller don't match the policies that we've implemented in PyTorch. And that's actually it. So like a bit of a wild walk through things I thought mattered in reinforcement learning. I hope you enjoyed it. In general, I would see this more as a starting point for questions. So if you do want to discuss some of these or want to tell me that I'm completely wrong about some of the things I said, I'm happy to talk to you. I'm still here till the end of the day. Also at the social event, please come talk to me.